I discussed this in the class. Okay, we analyzed this kind of spherical systems in the class. Okay, Q1 and Q2. Okay, we discussed this kind of spherical systems in the class. Okay, then after this, okay, I'm not gonna discuss this again. I gave, as I remember, I gave 2 homework, right? I gave 2 homework. Using that, I'll explain explain things again. Okay, so the first one was, as I remember, at the center you have plus q1 or minus q1. At the center you have plus q1 or minus q1. Plus q1, right? At the center you had plus q1, and here what did you have? Minus q2. Minus q2. And I think I gave that I mentioned that q1 is larger than q2, right? I mentioned that q1 is larger than q2, right? This was the system. Okay, I mentioned that q1 is larger than q1 is larger than q2. Clear? Okay, so in this system, okay, the first thing is the things out of the things that we learned last week. One of the main components is the induction. Okay, we were talking about induction, right? Can you remember induction? Yes. What is the problem? No. Okay, so we were talking about induction. So here, do we have to consider induction? No, right? Here we don't have to consider induction. What is the reason to not conduct induction? What is the reason to not conduct induction? Because this is a thin shell, right? Because this is a thin shell. Can you remember? Because this is a thin shell. So in that scenario, we don't consider induction. So we just write plain values and we add them. Okay, we just add plain values and we add them. That means if the distance to this point is r, if the distance from here to here is r, okay, if the distance from here to here is r, okay, if you write field intensity E1, if you write field intensity E1, you can write 1 over 4 pi epsilon. If I write the field intensity by Q1, I get Q1 over R squared. I just entirely forget this guy. And write whatever belongs to Q1, okay? 1 over 4 pi epsilon Q1 over R squared, right? Q1 over R squared plus, okay? 1 over 4 pi epsilon Q1 over R squared plus, then I would write 1 over 4 pi epsilon 1 over 4 pi epsilon. I entirely forget Q1, and if I had only minus Q2, okay, if I entirely forget Q1 and if I had only minus Q2, okay, if I had only minus Q2, okay, if I had only minus Q2, the field intensity here would be minus Q2 over R squared, right? Minus Q2 over R squared. Clear? So then you can write 1 over 4 pi epsilon R squared Q1 minus Q2. So what you do is, in a system like this, you like just superposition, okay? There's no impact from Q1 on Q2, or there's no impact from Q2 on Q1. So you entirely forget any impact they have between each other. So you write components individually and you just write the equation, add them. Clear? Just a superposition, okay? Just a simple superposition. Clear? Then at the same time, if you write the potential, okay, at the same time, if you write the potential V1, okay, if you write the potential, you can write 1 over 4 pi epsilon, 1 over 4 pi epsilon. Again, same scenario. Just write the things due to Q1 and Q2 again over R. Just write individual equations and add them, okay? Just write individual equations and add them, then you will get this, right? Okay. Then when you bring this to the surface, if the radius is capital R, when you bring this to the surface, no change happens to the system, okay? No change happens to the system. When you bring this to the surface, no change happens to the system. 1 over 4 pi epsilon 1 over 4 pi epsilon center plus q1 over, so I mean I just don't have to rewrite it again. From here to here you face the same equation, right? From here to here you face the same equation, so the only difference is simple r will eventually turn into capital R. That's all. Clear? Simple r will eventually turn into capital R. Clear? So you get q1 minus q2, q1 minus q2 over simple R squared. Clear? Then about potential, V2 1 over 4 pi epsilon q1 minus q2 over R. q1 minus q2 over R. Clear? 1 over 4 pi epsilon q1 minus q2 over R. Okay? Sorry, it should be now this should be capital R. Okay? This should be capital R, not just simple R. Simple R turns into capital R. Clear? Simple R turns into capital R. Clear? Got the idea? Okay. Then you write at the middle. Okay? So still the plan is this. Okay? Still the plan is this. You write individual contributions, then add them. Okay? You write individual contributions, then add them. Clear? So if the distance to here is also r, okay, if the distance to this point is also r, you would write 1 over 4 pi epsilon, 1 over 4 pi epsilon, charge is q1, due to q1, the field intensity is q1 over r squared, right? q1 over r squared. Clear? Do you have to write a field intensity due to minus q2? No, right? Why? If you forget q1, and if this is a system that you had only minus q2, this is within minus q2, right? Clear? It's inside the layer of minus q2. Can you remember? An outside layer will not create field intensity inside. Can you remember? An outside charge will not create a field intensity inside. So here the contribution from minus q2 is 0, right? Here the contribution from minus q2 is 0. Contribution from plus q1 is this. Clear? Contribution from plus q1 is this. Contribution from minus q2 is 0. Clear? So you get this one as field intensity. Okay? You get this one as field intensity E3. Then V3 potential, you get 1 over 4 pi epsilon. Writing potential is the complex thing here. So tell me if you had only minus q2, what would be the potential here by minus q2? Minus q2 over capital R, right? Can you remember? You do work only until the surface. Can you remember? You do work only until the surface against minus q2. After that, minus q2 exert no field on the object. Can you remember? So it's minus q2 over capital R. Clear? Then what is the potential by plus q1? What is the potential by plus q1? Here the potential by plus q1 would be 1 over 4 pi epsilon plus q1 over simple r. Clear? Plus q1 over simple r. Why? Against plus q1 you have to do work until here, right? Against plus q1 you have to do work until here. Clear? Then here you get 1 over 4 pi epsilon. Here you get q1 over r, then minus q2 over capital R. Minus q2 over capital R. Clear? q1 over r minus q2 over capital R. Clear? That should be the idea. Clear? So you just write individual contributions, then you add them. Okay, okay, that is the idea. Okay, write this down if you have to complete anything. So if I draw the graphs, okay, I'm not gonna give a lot of time because I asked you to try this. So all you have to do is do the corrections. So this is Q1, this is minus Q2. What happens with field intensity? What happens with field intensity is? What happens with field intensity is? Here outside you have Q1 minus Q2 over R squared, right? You have Q1 minus Q2 over R squared, right? Which is positive. Q1 is larger than Q2, right? So outside you have a positive field intensity going away like this, but it will decrease with distance. Okay, it will decrease with distance, so opposite direction, so positive negative, clear? But when you pass that and enter here, suddenly this minus q2 component disappears, right? Clear? Suddenly this minus q2 component disappears, right? Clear? So what happens is you just have a field intensity like this. Okay, you sure that these are the values I gave, right? Q1 and minus q2, right? And I gave that q1 is larger than q2, right? Okay, so what happens is when you pass here, when you pass the surface, suddenly minus q2 disappears, right? So initially you had q1 minus q2 over r squared, suddenly it becomes q1 over r squared, clear? Suddenly it becomes q1 over r squared, clear? So this minus component, it gets removed from the system. So q1 minus q2 over r squared suddenly turns into q1 over r squared, clear? That means the minus component goes out, a sudden increase of field intensity. Sudden increase of field intensity, clear? It creates a sudden increase of field intensity, clear? Got the idea? It creates a sudden increase of field intensity, clear? Clear? Got the idea? So this is different from the question I initially hoped. That's the issue. Like I initially hoped that q1 is here, minus q2 is inside. So in the tute that I'm giving to you guys, the tute that I'm distributing, I said that everything you write here will be given in a tute. That tute you will have a slightly different example. Okay, only for this you will have a slightly different example. So it will go like this here. It will go like this. Clear? Got the idea? Then when r goes to 0, it shows to infinity as usual. Clear? Okay, clear? Then what about potential? What about potential? Same thing. Same thing. uh, you have a positive potential. You have a positive potential. Clear? You have a positive potential like this, and another positive potential like this, another positive potential like this. Clear? Then this potential, okay, this potential increase like this. Okay, why? It's q1 minus q2 over r. Clear? Suddenly, initially it's q1 minus q2 over r. Clear? Suddenly this minus part becomes a constant. See, suddenly this minus part becomes a constant. Clear? Clear? Minus part becomes a constant. It stops gaining value, right? Suddenly this minus part becomes a constant. It stops gaining value, right? Only positive part increases now. Clear? Clear? Initially, when R decreases, both minus part and positive part increased. Okay? So you had a certain increase due to this difference between them. So whatever the increase of positive part minus whatever the increase of negative part, the remaining part would be the actual value that you get, actual value increased. Okay? But here what happens is, okay, here what happens is, in this scenario, you lose the positive part becomes, negative part becomes a constant suddenly. Now the positive part increases. Okay, that means it's a boost of increase, right? Initially there was a positive part growing and a negative part growing. Now the negative part becomes constant and positive part can grow easily now, right? So the rate of increase in the potential will suddenly increase. Okay, so there will be a sudden surge, increase of the gradient. See, sudden surge of increasing. Clear? Increase of the gradient, and it will shoot up to infinity when r goes to 0. It will shoot up to infinity when r goes to 0. Clear? Sudden surge of gradient you should get. Clear? Clear? Initially you were growing weakly because there was a positive component and a negative component both growing. Now the negative component becomes constant and now the positive part is only increasing. Clear? Which supports the system, right? Write this down. I mean, don't worry about writing everything. You will get the tute next week. Okay, everything will be included. Today also we have to write a lot of stuff, but everything will be included in the tute that I'm giving to you. So don't worry about writing tutes. Okay, focus on understanding things. Okay, ask questions and try focus on understanding things better. Okay, and the next example, as I remember, q1, q2, just confirm, q3, right? This was the next question, right? Radius was, I think, r1 and r2, right? Radius was r1 and r2, right? Okay, next one. Like this scenario, now it should be simple. Okay, now this should be simple. Now you know the idea. Write individual contributions, add 1 over 4 pi epsilon q1 plus q2 plus q3 over r squared field intensity 1 over 4 pi epsilon q1 plus q2 plus q3 over r. Just write the individual contributions and add. Clear? Okay, so if you had this q3 only as a sphere, what you write is 1 over 4 pi epsilon q3 over the distance from the center, right? If you had q2 only, q2 over r squared. If you had q1 only, q1 over r squared, you add them to get the overall impact. Clear? Add individual contributions and add them. Okay, so here also same scenario. This is E1 and V1. Then here E2, E2, E2. You get 1 over 4 pi epsilon q1 plus q2 q1 plus q2 over r squared, right? Why? q3 will disappear when you're writing field intensity, right? When you're writing field intensity, q3 will disappear, right? Clear? Impact from q3 will disappear when you write the field intensity, only q1 and q2, right? But what about potential? For potential, you have to write 1 over 4 pi epsilon. You had to do some work until the surface against q3. So there you write q3 over capital R2. But considering q1 and q2, it is only simple R. Or it is simple R. Clear? Considering q1 and q2, it is simple R. Clear? It is simple R. Got the idea? Then what about the next one? Here. Outside. What do you get here? Here you get E3 equals 1 over 4 pi epsilon. Sorry, not here, inside in the sense here, inside the object. 1 over 4 pi epsilon, no impact from q3, no impact from q2, just q1 over r squared, right? Just q1 over r squared. Clear? Then about potential, v3 1 over 4 pi epsilon, you have to do work against q3 until r2. Then you have to do a work against q2 until r1, until the surface, until r1. Then you have to do a work against q1 until the position you reach, right? Because q1 is at the exact center, right? So there you get q1 over simple r. Clear? You just write individual contributions, then you add them. Okay. I mean, I previously proved that if you have a charge outside, it can't affect inside, right? Impacts will cancel out. If you have a charge outside a ring, inside that ring, that charge have no impact. Clear? That charge have no impact. Got the idea? Hope now you have a good idea about thin shells. Okay, don't worry about writing a neat note. Okay, we'll provide that. So just focus on understanding things and ask questions if you have any doubts. Okay, now I'll give you another question. Try this. Okay. Okay, first of all, we had to draw the graphs, right? So it's quite simple, right? Q1. Now it's quite simple. Why? Q1, Q2. I'm not going to give a lot of time to write this down, okay? Because I anyways provide the note. If we draw the field intensities, okay? If we draw the field intensities now, okay? If we draw the field intensities, outside the sphere, Q1 plus Q2 plus Q3 R squared, suddenly it turns into, suddenly when you pass this, it turns into Q1 plus Q2 over R squared. That means sudden drop, but again increase, clear? Then again when you pass this point, again you lose Q2, again you lose Q2, right? So it becomes Q1 over R squared, another drop, clear? Another sudden drop, and now it reaches infinity. It reaches infinity when R goes to 0, clear? In this side, same thing, opposite direction. Same thing, opposite direction. Field intensity is clear. Okay, if you did this for 2 spheres, now you should have the idea about 3 spheres. Okay, nothing complex. Clear? Got the idea? Okay. What about potential? What about potential? Don't worry about writing. Okay. What about potential? What you get? What do you get when you consider potential? So when you get potential, it's anyways positive because all the charges are positive. So you anyways get a positive distribution. Okay. You anyways get a positive distribution. So it increases. It increases potential. It increases. Lose the contribution from one guy. So rate decreases. Again increases. Again increases. Lose the contribution from one guy, again increases. Clear? So it stops where it starts where it stopped, because a component does not disappear, but the support from one guy it loses at each boundary, right? Here it loses the support from Q3. Q3 doesn't support the growth after this point, right? Potential by Q3 becomes a constant after this point. Can you remember? After this point, potential by Q3 becomes a constant. Only these two supports in growing the potential, right? So see, its gradient suddenly decreases. Clear? Sudden decrease of gradient. Clear? The rate of increase of potential drops. Clear? Then again it grows. Again rate of increase of potential drops. Then again it grows. Clear? It grows. Rate decreases due to lack of one component. Again grows. Now another component becomes constant. Clear? So only the growth changes here. No sudden drop like this. Clear? No sudden drop like this. Clear? Okay. And talking about now, the next example I need you to try is this. Okay. Hope you can remember theory. This one. You place a charge Q1 here, and there's a conducting shell outside, but this time it's not a thin shell. Okay. This time it's not a thin shell. This time it's not a thin shell. Clear? This time it's a thick shell, not a thin one. Clear? Got the idea? Internal radius is R1, external radius is R2. Clear? Now and we are giving another charge Q2 to this. Clear? I'll help with the first step. First thing is you have to consider induction in a thick shell, right? Clear? First you have to consider induction, right? In a system like this, you definitely have to consider the induction, right? Clear? You definitely have to consider the impact from induction. Clear? So plus Q1 will create a minus Q1 induction here. That minus Q1 will create a plus Q1 induction here. Clear? So after considering the induction, this one will Q1, this layer you have minus Q1. Clear? This layer you have Q2 plus Q1. Q1 from induction, Q2 it originally had, right? Q2 it originally had. Clear? I need you to try, okay? I mean, it's okay to get this wrong because anyways I have to teach this part, but I need you to like work and play around with your existing knowledge to understand this. Try to write the field intensity and potential here, here, and here. Consider the distance as simple r. Okay, consider the distance as simple r to all 3 points and try to write field intensities and potential at these 3 points. Okay. Okay. So considering this system, okay, considering this system, this one, uh, like now we are capable of handling a system like this using the existing knowledge, okay. We are capable of handling this system using the existing knowledge we already have, okay. How? I mean, just think about this point. I mean, when you're considering an outside point, all the charge inside you consider as a point charge. Can you remember? The whole charge inside you consider as a point charge when you're writing values for an outside point, right? Clear? So the field intensity here, E1, would be 1 over 4 pi epsilon. 1 over 4 pi epsilon. Clear? Here, what do you get when you add all the charges? Q1 minus Q1, Q2 plus Q1, everything. When you add everything, plus Q1 minus Q1 cancels out. Plus Q1 minus Q1 cancels out. You get Q1 plus Q2, right? You get Q1 plus Q2. So you get Q1 plus Q2 over R squared. See? Clear? And potential again 1 over 4 pi epsilon Q1 plus Q2, Q1 plus Q2 over R. Is that clear? Clear? So writing it is quite simple. Clear? Then if you write the values at the surface, same scenario continues, right? Same scenario continues until the surface, right? Clear? So the field intensity would be at the surface 1 over 4 pi epsilon. Again, same scenario, simple r will eventually turn into r2. That's all, right? Simple r will turn into this distance r2, right? That's all. So you get q1 plus q2 over r2 squared. Then potential V2 1 over 4 pi epsilon q1 plus q2 over r2. Clear? Q1 plus q2 over r2. Clear? Okay. Okay, this is E2 and V2. Clear? Then inside the conductor field intensity should be 0. Can you remember this point? Inside a conductor field intensity should be 0. There can't be field lines inside a conductor. Can you remember that point? There can't be field lines inside a conductor. Clear? So E3 is 0. Clear? E3 is 0. There's no field inside the conductor. Clear? There's no field inside the conductor. E3 0. Clear? E3 0. Okay. E3 is 0. Then what about V3? What about V3? Inside a conductor there's no field. So you don't have to do a work inside a conductor. So the potential inside a conductor will be equal to the potential at the surface of a conductor. Can you remember? I mean, still we are not learning this properly. We are just playing around with our existing knowledge to come up with answers. Okay, that's what we are doing now. Okay, we are just playing around with our existing knowledge to come up with answers. Okay, so here also your field intensity, here your potential will be equal to the potential at the surface, right? It will be equal to the potential at the surface, right? Why? In a conductor you don't have to do any work, so you do work only until the surface. Clear? Only until the surface. So the potential inside the conductor will be equal to the potential at the surface of the conductor, right? Clear? So you just write 1 over 4 pi epsilon q1 plus q1 plus q2 over r2. Same thing as the surface. Clear? But after that an internal point, for an internal point writing field intensity is very simple. Why? any outside ring will not provide a field intensity here, right? Any outside ring, clear, will not produce a field intensity here, right? Clear? So the field intensity only Q1 will create a field intensity here, okay? Only Q1 will create a field intensity here. So E4 1 over 4 pi epsilon Q1 over simple R squared, no impact from outside rings, okay? No impact from outside rings, clear? Okay? Outer charge can't create a field intensity inside, clear? The story here is, okay? The story here is that like it's not there's not gonna be any like complexities. I mean, yes, there are complexities, still we haven't learned the actual theory part how to do that, but we can manage a large portion of the question from our existing knowledge, okay? We still don't know an actual method, but there are theory items we learned here and there, right? Yes, when you consider outside, consider everything as a point charge, inside a conductor no field, like that. From the theory items we picked up here and there, using them we can like manage a large part of a question, okay? But here also when you're writing potential there will be some doubts, okay? How are you going to write the potential? So how are you going to write the work done from here to here? Clear? Okay, you can write the potential up to here, you can write the potential inside the conductor. How are you going to write the remaining part? There are some sort of small complexities like that, clear? Small complexities like that, but you can handle a large part using your existing knowledge, okay? But the problem is sometimes they may give much complex questions, like they will give you another shell outside this, okay? Another shell outside this, give different charge to different points, clear? You will have a positive, minus, another negative charge here and there, okay? The question may turn, they can have the ability to turn the question into a very complex system, okay? So just from the theory we learned here and there, if we are thinking of handling this, it can be quite challenging if they make the question much complex than this, okay? Clear? So you already did this, okay? You already did this. I think, I hope the way everyone got the answer in the way that I'm gonna do now, you did that without knowing that it is correct. That means when you get a thick shell like this, okay? Okay. When you get a system like this, if you have plus q1 at the center, if you have plus q1 at the center, now if you have already considered induction, okay? If you have already considered induction, here you have q1, here you have minus q1, here you have minus q1, then here you have q1 plus q2, here you have q1 plus q2, clear? Here you have q1 plus q2, clear? When you consider this system, you are, it's entirely okay to consider this as a thin shell system and do the question, okay? That means when you get a thick shell, okay, first you consider induction, okay? First you consider induction, q1 minus q1, q1 plus q2, clear? Then you entirely forget that it is a thick shell, okay? You consider it as a thin shell. You just convert this into two thin shells, then do the question as usual, clear? That's why I was waiting on thin shells, doing a lot of questions on thin shells, because after this point we may have to work with lot of different scenarios, okay? But the method that we are going to use is whatever the system, okay, no matter how complex the system is, okay, whatever the system and no matter how complex the system is, clear, no matter how complex the system is, we are going to use we are going to use we are going to first consider the charge distribution. After writing the charge distribution properly, we are going to consider them as thin shells and we are going to do the calculations, okay, clear. Then it is much easier. Now see, you will get the same answer, okay. Consider here, right field intensity, 1 over 4 pi epsilon. You write the field intensity by plus q1 minus q1 plus q2. When you add everything, you will get q1 plus q2 over r squared, right? No difference, clear. You get the same answer, clear. Then what about the potential? V1, again you add everything, 1 over 4 pi epsilon q1 plus minus q1 plus q1 plus q2, you get q1 plus q2 over the internal radius was r1, external radius was r2. You write r2, you write simple r, clear, clear. Then inside, see, inside you write the field intensity. Now what is the field intensity? See, 1 over 4 pi epsilon, there's no impact from outward charge. You have plus q1 then minus q1, right? See, plus q1 then minus q1, right? So when you write it, plus q1 minus q1 over r squared, which means you eventually get 0 and that is the correct answer, right? See, you eventually get 0 and that is the correct answer. See, when you consider it as a system of thin shells, you still get the exactly correct answer, right? Clear? Then what about the potential? What about the potential V3? Same, 1 over 4 pi epsilon, 1 over 4 pi epsilon, okay, 1 over 4 pi epsilon, potential would be q1 minus, again, potential would be, you first write the potential by q1 plus q2 charge. Consider it as q3. Consider it as q3 and you first write the work done against q1 and q2 until its surface, okay, clear. Then you write q1 plus q2 until the surface, which means r2. Consider it as q3, okay, q3 over r2, clear, q3 over r2, clear. Then you write the potential by this plus q1, then you write the potential by this minus q1, they will cancel out, right? Why? You write 1 over 4 pi epsilon plus q1 over r, then you will write 1 over 4 pi epsilon minus q1 over r, right? These two will cancel out, clear. These two will cancel out, clear. Plus q1 over r and minus q1 over r will cancel out, see, clear. See, you get the exactly correct answer, right? See, the potential at the surface is the answer, right? Got the idea? So yeah, anyways, getting the correct answers, okay. Got the idea? Then inside also, what is the field intensity? Any outside ring have no impact. No impact from q1 plus q2, no impact from minus q1, only from plus q1. 1 over 4 pi epsilon q1 over r squared, clear. 1 over 4 pi epsilon q1 over r squared, clear. Now we don't have that confusion about writing the potential, right? Because it is just a thin shell system, right? Consider this as q1, this as q2 and this as q3, okay. So you don't have the confusion of writing the potential. You first write 1 over 4 pi epsilon, then against q1 plus q2, you write until the surface, right? You write until the surface, clear, which is r2, clear. against q1 plus q2 you write until the surface, clear? Then against minus q1, against minus q1 you write until that surface, clear? Against minus q1 you write until that surface, clear? Which is r1, which is r1. Then against plus q1 at the middle you write until this point, symbol r, clear? Clear? Now you don't have that confusion. You just write induction, consider induction, then you consider this as q1, this as q2, and this as q3. Then you simply write answers, clear? Got the idea? Then you simply write answers, okay? Write this down, but don't worry about writing a neat note. Write things for the sake of understanding things, okay? Don't try to maintain a neat note. I'll provide everything as a tute. Everything you write in this lesson, throughout the lesson, I'll provide at the end, I'll provide as a full tute, okay? I'll provide it as a full tute. Everything you write in this lesson, I need you not to worry about that, but to focus on like writing, like for the sake of understanding things and remembering things. Clear? Got the idea? Okay. Now try to draw the field intensity graph and the potential graph quickly. Try to draw the field intensity graph and potential graph quickly. Try to draw the field intensity graph and potential graph quickly. So in online students, just mention like what are the issues you have on Mondays, okay? Because we initially planned to move the English medium class to Tuesday, But now there's a problem. Chemistry teachers ask him for Tuesdays, and like and again like the Sinhala medium classes are yet to placed on Tuesday morning. Sinhala medium revision classes. So so they are requesting for that too. So so one solution is to move it from Monday morning, because this is the time that we are placing as the permanent revision for English medium students. So even the other students may sometimes move to this class after we finish theory and all as the revision class. So we need a permanent time for revision. So for now, according to the other teachers and all, the possible permanent time for revision is Monday morning. Initially it was Thursday morning, but now English medium chemistry people mentioned that they will place their revision and paper classes on Thursday morning too. So what is left for physics for English medium? For Sinhala medium, it's quite stable. No changes in that. For English medium, as per English medium timetable, what we can allocate is Monday morning. So most probably, I mean, can't change that because there are conventions about that. There are conventions about that. Even the Wednesday evening, the class that I'm doing now is not following the conventions. Why it's not a physics time? But I mean, no, I mean, we don't have to care about that because we don't have a lot of students. Sunday morning was the official physics time for this batch. So that's why I'm doing my main class on Sunday morning. So I think we have to place a permanent revision time on Monday morning, which will continue until then. It will continue until A levels. Okay. So I think we may have to move the class to Monday morning. Okay. We may have to move the class to Monday morning as the normal class, and within 3 months I'll be done with the syllabus. Within 3 months I'll be done with the syllabus. Then we'll convert this into the permanent revision class. Okay, that is the plan for now. We'll convert this to the and maths and all Friday mornings. So what is left for physics revision is Monday morning. And I'll be conducting, most probably I'll be conducting a Sinhala medium revision too. It will be on Tuesday morning then, because it will be on Tuesday morning or Thursday morning, because that is the Sinhala medium physics revision date as per conventions. So I think we may have to move this to Monday morning. Okay. And now currently we have a Monday night paper class discussion at 7. Okay. So I think anyways the students who have classes on Monday evening, they are anyways not capable of joining the paper discussion, right? On time. So if that is the case, I'm planning of moving the paper discussion to Monday evening too, because then the students can directly stay for the revision one. After 3 months they can directly stay for the revision class, maybe write the paper within 2-3 hours, stay for the paper discussion, done everything done in one day, then go home. Okay, things happening in one day would be quite hectic for now for you guys, but when it is closer to A levels, finishing off everything in one day, finishing everything in one day and going home would be a quite relief, because you have more days to stay at home then. Okay, so if you can stay for the revision in the Monday morning, write the paper class Monday evening, stay for the paper discussion after that, finish everything. Otherwise, you do these three things in on 3 days, right? Okay, but anyway, Sunday morning theory class will continue to happen. So you have the ability to join that. And the heat sessions will be doing on Monday morning as usual as a full 6 hour class, but still you have another option of Thursday night class. Okay, Thursday night also I'm doing heat. Okay, so you have all the options. Monday morning class, one full class, maybe 5-6 hours full class. Then Monday, then or Sunday morning English class, or Thursday night heat class. Okay, so you have all these options. Choose whatever you like and you can join. Okay, that would be the plan that we have to continue according to conventions. And it will be permanent. After that, it will be permanent. And anyways, we'll be done with the syllabus within 3 months. then you definitely have to join the paper class. Okay, so and the plans may change a bit, like I'll sometimes may increase the time and do some stuff to quickly finish the syllabus. Okay, properties of matter theory we finished today. This Friday also you have a properties of matter session, you can join if you like. Okay, the English medium one. Okay, then within this week we are done with properties of matter 2. Then after that we have to do a similar seminar for matter and radiation, and in the main class we can keep doing and we can finish electronics, magnetics and electrical. That's all. So quite enough time we have, like we can finish everything within 3 months. That should be the plan. So have you written the are you done with the graphs? Are you done with the graphs? This one, q1, here you have plus q1, here you have uh, I think minus q1, here you have q1 plus q2, right? Here you have q1 plus q2. Clear? Clear? Ah. So in this case, so in this case, uh, outside the field intensity is just like this, just like this. Then it dropped to 0, right? This is inside the conductor, right? Inside the conductor field intensity drops to 0. Clear? Then are you starting from here or here? You can't exactly tell. You have to do a calculation for that. Okay? Why? Until the surface, it was q1 plus q2 over simple r squared. Okay? Then you stop here. Then you stop here at 1 over 4 pi epsilon q1 plus q2 over capital R2 squared. Then 0. Then 0, continuous 0. Then you suddenly start here. With 1 over 4 pi epsilon q1 over r squared. Clear? You lose this q2 component. Okay? You stopped with q1 plus q2, but you again start with only q1. But the distance, you stopped at r2 squared. Now you are starting again at r1 squared. Clear? Distance decreases. You lose one charge, but distance decreases, which again increase the field. Okay? So you lose one charge. Here you stopped at q1 plus q2, but you are starting with only q1 when you are writing the field again. So there's a disadvantage with the charge, but there's an advantage with the distance, right? Here you stopped at capital R2 squared. Now you are starting at again capital R1 squared. Clear? There's an advantage from distance. So you, without doing a calculation, you actually don't know whether the field here is larger than this or not. Clear? So you just can use whatever the graph you like. You can start from anywhere you like. Okay? You can start from anywhere you like and it will keep increasing until infinity here. Clear? Again you meet q1, when you are really close to q1, it will shoot to infinity, right? Clear? In this side also the same scenario goes like this, drop to 0, then start somewhere and go to infinity when the distance is 0. Clear? Clear? Then what about the potential? Then what about the potential? What about the potential? What about the potential here? So write in the potential. Outside you get q1 plus q2 potential. Clear? Inside the conductor it is constant. Inside the conductor it is constant. Clear? Inside the conductor it is constant. Although I draw this as thin shells, this is a conductor, right? So inside the conductor potential is constant. Then again when you pass this and start moving towards q1, it starts growing. Okay, it starts growing. Clear? This is the potential distribution. Got the idea? Clear? So we are just analyzing different questions now. Okay, different methods of questions. Okay, how I mean, now we are done with the main theory part here. Now we are analyzing how can we get questions. Okay, clear? First of all, sorry, this should be minus q1, right? This should be minus q1. This should be minus q1. No. Here, the potential is this, right? Then it becomes constant from here to here. Clear? Then it becomes constant from here to here. Then you again start from here, right? Then you again start from here. So yeah, again starting from R1, right? Yeah, again starting from R1. Now see, uh, when you put R1 here, see, Q1 over R1, these two cancels out. You again start from the surface value. Clear? You again, you again start with the same value you had at the surface from here, right? See, at the surface you had Q1 plus Q2, sorry, Q1 plus Q2 over R2. At the surface you had Q1 plus Q2 over R2. Clear? Then again here you start with what? Again here you start with R1. So this is the potential inside this part, right? So here when you put R1, this one and this one suddenly cancel out. Then you again, you are left with 1 over 4 pi epsilon Q1 Q2 over R2, which is the same potential you had here. Then only it starts changing, okay? Then only it starts changing. So you start from the same constant value, then again you start increasing, okay? Got the idea? You may have to analyze these things, write these things, go home and try to write these things alone, okay? Okay, that's why I'm giving the tute later, okay? That's why I'm delaying the tute, okay? Okay, I need you to try to understand these things, try to do these things alone, okay? And try to come up with answers, clear? Okay, got the idea? Got the idea? Clear? Okay. Need me to increase this? Okay. Okay. So, clear? Got the idea? Okay. Just ask questions, okay? I mean, I can't go really slow in this area, but these areas may be confusing, okay? So ask questions, okay? Otherwise, I don't know whether I should explain things again or not, okay? So ask questions as much as possible, okay? Don't worry about writing a note. We'll provide that. Try to understand things. Ask as much questions as possible to analyze things and try to understand things, okay? So next one, another possible thing that you can see in a question, okay? I'm going to show you how can you get questions, okay? So another possible thing that you can see in a question is this. Another possible thing, you have a you have two conducting spheres like this. You give a charge of q here. You give a charge of q1 to this, okay? You give a charge of q1 to this, clear? Then you ground this. Then you ground this, okay? When you ground the surface, Earth will send some kind of a charge to this surface, right? And what would be the potential here? 0, right? Okay. Now these are not actual theory. These are just different scenarios you can see in questions. Okay, but in the tutor I'm giving, I'll provide you topics here. Okay, what happens when you earth something like that? You will have proper topics and everything. So don't worry about writing topics and writing everything. Just do these things as questions. Okay. So just now try to find the charge. If the radius here is A, if this radius is B, try to figure out the charge that appear on this surface. Then the next scenario, you give a charge q1 to this, you give a charge q1 to this and earth this guy. Clear? Then find the charge that appears on this one. Clear? When you connect a system to earth, earth will send some kind of a charge. Clear? I need you to find the charge that would come to here and here. Clear? The the point that you have to think is earth will send a charge until the potential here is 0. Clear? Here also earth will send a charge to this surface until the potential here is 0. Clear? So this is the question. Just put the charge here as simple q and try to find q. Okay? Assume that the charge sent by earth is q and try to find q. Okay? Just write this as questions. Okay? Don't write down a topic. Don't try to write a question. Just put down the diagram and try to get answers. And again, one more thing to add. After drawing these stuff, you should be able to draw the field intensity lines too. Okay? Field model. Even the field model is available in your tute. Okay? Even the field model is available in your tute. What happens is, out from q1 plus q2, you have field lines like this. Okay? Out from q1 plus q2, you have field lines like this. Clear? Then here you don't have a field, right? Then here again from q1 to minus q1, you have some field lines. Clear? Clear? Here you have q1 plus q2 both. So you have more field lines here. Outside you have more field lines. Inside you have less field lines. Clear? Then in this scenario, like in these scenarios also you should be able to draw field lines. Okay? In these scenarios also you should be able to draw field lines. Okay? This one. Okay? How? How? In this one? In this one? You have field lines going from Q1. You have field lines going out from Q1. I'll draw it here. In the previous example, you had Q1 minus Q2, right? So here you have field lines going out. Here you have field lines going from Q1 out. Inside it is just Q1. Field lines just by Q1, clear? But outside it becomes Q1 minus Q2, clear? Outside it becomes Q1 minus Q2, clear? So you get a lesser number of field lines out, right? Here you have only Q1 over R squared, a stronger field. Outside you have Q1 minus Q2 over R squared, clear? Clear? So a lesser number of field lines you draw outside, clear? So you should understand these things and try to draw field lines too, okay? But in the tute I'm giving to you, everything is included, but you should have the ability to understand these things, okay? Clear? Why? A stronger field means more lines. So Q1 over R squared means more lines. A weaker field means less lines, clear? So less number of lines out, more number of lines in, clear? Like that you should have the understanding, okay? You should have the understanding like that too. That means these are separate theory points, okay? But when required, you should be able to combine them, okay? These are entirely separate theory points, but whenever required, you should be able to combine them and analyze them as a whole. Back to the question. Try to get the answers quickly. Try to get the answers quickly. Okay, what happens here is just write the potential and make it 0. That's all. That means if you have Q1 here and simple Q here, what is the potential here? You just add them. Just consider them as thin shells. 1 over 4 pi epsilon. Q1 over distance to this point is B. Then again 1 over 4 pi epsilon. 1 over 4 pi epsilon. Here the charge is simple Q. Charge is simple Q. Distance to here is B. And the sum will be 0. Resultant potential should be 0. Clear? So 1 over 4 pi epsilon cancels out and B cancels out. You have Q1 plus simple Q equals 0, which gives you simple Q equals minus Q1. Clear? You get simple Q equals minus Q1. Clear? Got the idea? You get simple Q equals minus Q1. See? Just write that's why we try to figure out thin shells first. After that, for everything in systems like this, we would use the concepts that we use for thin shells, okay? Just the way we wrote potential for thin shells, okay? You use the same thing here. Okay. What about this simple q? What about this simple q? Just write the potential here. What is the potential here? This is A, this is B. When you are writing the potential here, you will get 1 over 4 pi epsilon, 1 over 4 pi epsilon. You do work against Q1 only until this surface, right? Only until this surface you will do a work against Q1, right? That means only until B, clear? Only until B. Then you will do a work against simple q, 1 over 4 pi epsilon. You will do a work against simple q until A. Until A. Until A. Clear? And at the end of the day, when you write the potential as a sum of this, as a sum of the potential by simple q and capital Q1 both, the resultant will be 0. Clear? Resultant potential should be 0, because that's the whole point of connecting something to earth. Clear? Making the potential there 0. Clear? Then you multiply it by 4 pi epsilon b. So sorry, you multiply it by 4 pi epsilon. Then you get q1 over b plus simple q over a equals 0. Clear? Clear? Then you get simple q equals minus q1 a over b minus q1 a over b. Clear? That is the charge that may appear here. Clear? Clear? Got the idea? So these are just small questions that may support you in handling other questions, okay? Not actual theory parts. Because I mean, you should be able to do this using the theory parts you already know, right? No new theory part here, but anyways, it's difficult to like combine things and come up with conclusions like that, right? Without teaching. So that's why I'm teaching, okay? Otherwise, these are just conclusions from the theories that you already know. Okay. Another small question. Another small question. Hope this is okay, right? So these are just questions that I can ask from the theory that you already know, okay? So I have a plus q charge here. You have a conductor here. You have a conductor here. Just a conductor, not charged, just a conductor. I need you to graph the field intensity from here to here. I need you to graph the field intensity in this line. I need you to graph the field intensity in this line. Clear? Graph the field intensity in this line. There's a question in the first diagram why it is not q1 over a, because when you are considering the outer surface, when you are writing the potential here, it is simple q over b and q1 over b, right? When you are considering the outer surface, it's simple q over b and capital Q1 over b, right? When you are writing the potential here, you write the distance to that, right? So that's why in that case, it's just q equals minus q1, okay? But in the second scenario, it's different. In the second scenario, when you write the potential here, you have the impact from q1 only until the surface, okay? Then from the impact from simple q, you have to write until here. Clear? Got the idea? Try this question. We'll give you some time. Try this question. Try to analyze things properly. Try to remember all the theory points you learn. Combine them and come up with the answer, okay? Don't just draw graphs, okay? Try to come up with actual answers. Try to remember the theory points. Think what are the things learned about induction. So you have to consider everything, okay? You have to consider everything. Consider everything in the sense, first consider the induction, okay? Then draw the graphs, okay? That means it's like this. If you didn't have this conductor, if you didn't have this conductor, the graph would look like this, right? If you didn't have this conductor, the graph would look like this. The graph would look like this. Clear? The graph would look like this. Clear? But this conductor, what happens is, due to this charge, negative charge attracts towards this side and positive charge attracts towards this side, right? Clear? So the whole potential in this side may decrease a bit than the original value due to this additional negative charge, right? The whole potential in this area will go down a bit due to this negative charge, right? Due to this negative charge, it will go down a bit. Clear? Then here you have a positive charge. This potential is due to this positive charge. Now you have an additional positive charge too. Clear? Due to this additional positive charge, the field intensities may increase a bit in this side. Clear? Clear? Then what actually happens is the this side will go down a bit. Clear? And this side may go up a bit such that the field intensity from here to here becomes constant. Sorry, potential from so we are first drawing the field intensities. Next I need you to draw the potentials too, okay? Next I need you to draw the potentials too, okay? Clear? So what may happen is, okay, okay, field intensities, okay? But the field intensities here, I was talking about potential. Sorry, I asked you to draw the field. Okay, okay. So the explanation should change a bit if I'm drawing the field intensity first. I actually needed you to draw the potential. Okay, so draw potential too, but I'll teach from field intensity. Okay, I'll start from field intensity and move forward. Things should change a bit, but I originally needed you to draw the potential only because the field intensity is a bit complex here. Okay, field intensity is a bit complex here. So what happens is, okay, you have the charge here. So drawing the field intensity should not be that complex. Okay, yes, field intensities may change a bit, but here inside the conductor you can't have a field intensity. Clear? Inside the conductor you can't have a field intensity. Clear? That's all you have to remember. When drawing field intensity, it is simple. Inside the conductor you don't have a field intensity. Clear? Then in this side you have infinity here, okay, and a certain field intensity in this side. Clear? And a certain field intensity in this side. Clear? Then again you will have a certain field intensity in this side. Clear? That's all. No major changes for field intensity. Okay, no major changes for field intensity. Clear? You just have a zero region here. Without knowing this length and charge distribution and all, you can't talk about the magnitudes. Okay, without knowing the charge distribution, actual charge distribution, and this length and this distance and this distance, without writing equations, you actually can't know the value you stop here and value you start here. So it just you have to know is it will drop and there will be a zero field intensity here. Then again the field intensity may start here. Inside a conductor there's no field intensity. That's all you have to remember. Okay, that's all you have to remember. Clear? Drawing the field intensity is simple. This is the source of all the field. So field intensity drops. When it is further away, it again drops. Okay, when it's further away, it again drops. Clear? But uh, there should be zero field intensity inside the conductor. Okay, clear? So writing the field intensity is simple like this. Okay, it's not actually simple. It's too complex, so we can't actually write everything properly. Okay, All only thing that they, if they give a question like this, only thing that they may check is that whether they will check whether this is 0 or not. Okay. But for potential, you can draw actually. It was a mistake from my side. I actually needed you to think about the potential, because the potential distribution is quite nice. Potential distribution is quite nice and quite certain. If you had potential, it will go like this, right? It will go like this, clear? But now in this side, due to this negative charge, potential may decrease a bit, right? Why? You have a positive charge and a negative charge, clear? A positive charge will provide a positive potential, negative charge will provide a negative potential. So the potential may go down a bit, clear? Then in this side you have a positive charge, another positive charge. So due to the impact of both positive charges, potential will may increase a bit, clear? Clear? Then what actually happens is, what actually happens is, uh, this is the original graph without the conductor. This is the original graph without the conductor. What actually happens is, in this side, potential decreases a bit, clear? In this side, potential increases a bit, such that this part becomes constant. Why? In a conductor, potential is constant, right? In a conductor, potential is constant, clear? Throughout a conductor, potential is constant, right? So this side may go down a bit, this side may go up a bit, but here it will be anyways constant, clear? Here it will be a constant potential, clear? And here potential will decrease a bit in this side, potential will decrease a bit than the original graph, and potential may increase a bit than the original graph, clear? But everything happens, this decrease and this increase, everything happens aiming a constant potential here, clear? Everything happens aiming a constant potential here, clear? Everything happens aiming a constant potential here, because that's the whole target of induction. Okay, conductors face induction for what? Conductors face induction to keep their potential same at all the points, clear? Clear? That's the whole target of induction, clear? Induction happens because the conductors need to keep a equipotential surface everywhere, clear? Ah, okay. So next we have to go for capacitors. Okay, next we have to go to capacitor, and next week plan I'll inform, because from next week onwards new plans are starting. But the problem is, some students have extra classes on Monday. Okay, this Monday some online students also mentioned this Monday you have some extra classes, right? Okay, some online students also mentioned, so I'll check that and let you know what happens on this Monday. Okay, otherwise we can go change the plans from this Monday onwards. Okay, we can change plans from this Monday onwards. I'll let you know after the interval. I'll check everything and I'll let you know. Okay, yeah. So and I'll mention everything in the group. Okay, so be here by maybe 5:20. Okay, be here by 5:20. I'll directly start with theory of capacitors. Okay. uh, let's start with the discussion. Next we have to learn about capacitance. Okay, next we have to learn about capacitance. Well, static electricity to English medium. Okay. uh, so talking about capacitance, another major topic in the syllabus. Okay, this is another major topic in the syllabus, talking about capacitance. So capacitance means how much of a charge can a conductor hold. Okay, how much of a charge can a conductor hold? That is the whole idea of capacitance. Okay, like usually the like it's same as capacity. Okay, how much of a charge a conductor can hold. Okay, so if you have a conductor like this, okay, if you have a conductor like this, if you have a conductor like this, okay, and if the charge is q, if the charge is q, okay, I mean if you have a conductor like this, how much of a charge can you give to this one? Okay, how much of a charge can you give to this one? That is the idea. Clear? How much of a charge can you give to this one? Okay, that is capacitance. Okay, but the thing is, talking about capacity or capacitance, actually there's no actual limit for the charge you can give to an object, right? That means we have done different examples. You can give whatever the charge you like to this, right? You can give whatever the charge you like to this. Clear? So there's no actual limit of charge that you can give to a object. Okay, there's no actual limit. Clear? There's no actual limit for a charge that you can give to an object. Clear? Clear? uh, so there's no actual point of talking about a term capacitance, right? In that case, I mean, if you can give whatever the charge you like to any object, there's no point of talking about that, right? Capacitance, term capacitance, no. I mean, but the actual requirement here occurs, okay? The actual requirement here occurs as you give a charge, okay? As you give a charge to an object, its energy increases, and the more charge you give, more energy you need, right? Why? When you give charge to this, its potential increases, right? When you give charge to this, its potential increases, right? So when you give more charge, its potential increase further. So to bring the next bunch of charge to this, you have to do a lot of work, right? So the more charge you bring in, the more potential goes up, the more energy you have to waste on this. Clear? More energy you have to, more energy you have to waste on this. Clear? Clear? You have to waste a lot of energy. Clear? Ah. So the actual limitation is not about the charge, the amount of energy you need to produce, amount of energy you have to waste to give that charge to the system. Clear? So the limitation is from the side of energy or the potential. Clear? It's not about the charge, it's about how much of a potential is there when you try to give a certain charge. Clear? So we properly define capacitance as the amount of charge you give for a unit increase of potential. Clear? This is a unit change of potential. This is the charge. Clear? This is charge over potential. Clear? That means the amount of charge you should give. Okay, the amount of charge you should give per unit potential. Clear? Amount of charge you should give per unit potential. Clear? Clear? So it's C equals Q over V. Clear? C equals Q over V. Clear? That means amount of charge per unit potential. Clear? So that is the actual definition of capacitance. Now you can see it is Q over volt. That means coulombs per volt. Okay, but we give a single name for capacitance. It is farad. The unit for capacitance is farad. Clear? This is the SI unit for farad, unit for capacitance. Clear? But usually farad is a huge value. Okay, farad is a huge capacitance that you usually never see in real life application. So many values you see in questions will be in microfarad. Okay, many values you see in questions will be in microfarad. Clear? Okay, so now you have this. Okay, is this clear? Okay, so this is a equation that you can apply for any object. Q equals EV. You cross multiply, Q equals CV. This is a equation, very common equation that we will be using a lot. If you know the capacitance, if you know the voltage, then you know the charge that you should give to get that potential. Clear? Clear? Q equals CV. Got the idea? Okay. Okay. The next topic is, again, the limitation is in energy, right? Limitation is in energy. So what matters a lot is how the energy changes when you give a charge to an object. Okay, how the energy changes. Okay, okay, so like if the potential at a point is v, if the potential at a point is v, what is the amount of work or the energy stored when you bring a q charge to this point? If the potential is v, if you bring a q charge here, what is the energy required for that? Or what is the energy stored in that scenario? E equals VQ. Can you remember? E equals VQ. This is the work done, right? This is the work done or the stored energy. If the potential at a certain point is V, if you bring a charge Q there, the energy is VQ. Clear? The energy is VQ. Clear? But now the system that I'm going to analyze is not that simple. Why? It's not. I'm not bringing a charge Q to a potential V. I'm not bringing a charge Q to a potential V. I'm actually bringing a charge Q. I'm actually bringing a charge Q. Okay. I'm bringing a charge Q, and that charge Q itself produce this potential, right? Here. And that charge Q itself produce this potential, right? Here it's a bit different. Initially there's already a potential here, and I bring a charge Q here, which produce an energy of VQ. Clear? But here I bring a charge Q, and the potential is produced by that charge Q, right? Potential is produced by that charge Q. Clear? Got the idea? It's quite different. Okay. So what would be the energy stored here when I bring a charge Q to this? What will be the energy stored here when I bring a charge Q to this? So the Q equals EV equation we have. Then V equals 1 over C Q. V equals 1 over C Q, right? V equals 1 over C Q. Clear? Then you take a system, okay? You take a system and you take a system and you keep bringing charge to this, okay? You keep bringing charge to this. That means the graph you analyze is, q v. When q is 0, v is 0. Okay, clear? When q is 0, v is 0, right? Clear? When the charge is 0, potential is 0. Clear? There's no potential when there is no charge. Clear? When q is 0, v is 0. Clear? Clear? But when you bring more charge in, the potential increases according to this, right? Clear? When you bring more charge in, when you bring electron by electron, potential increases according to this, right? Clear? When you bring electron by electron, potential increases according to this. Clear? Potential increases like this. Clear? Then here the charge is q1. If I bring a charge of q1, if the potential then is v1, what is the energy stored in this process? Now you know that energy could be obtained by vq, right? Clear? So in this scenario, okay, in this scenario, at this potential, you bring a charge of q1 like this. That means this is the vq at that point, right? Clear? Then in this potential, you bring this charge. So that is the work done for that, this area. At this potential, you bring this charge. So that is the work done for that. So the continuous multiplication of VQ gives you the total energy or total work, right? Clear? Continuous multiplication between V and Q. Clear? Continuous multiplication between V and Q gives you the energy. Clear? Clear? Continuous multiplication between V and Q gives you the energy. Clear? So the energy here is half V1 Q1, right? Half V1 Q1. Clear? Here energy stored is half V1 Q1. Clear? Clear? Okay. Energy stored here is half V1 Q1. Got the idea? Clear? So if you like, you can replace this V1 Q1 like this, using this Q1 equals CV1. Clear? So if you like, you can write half V1. Instead of Q1, you can write CV1. Clear? Instead of V1, you can write CV1. Clear? Then you get half CV1 squared. Clear? Half CV1 squared. Clear? Then again, if you like, half Q1. Instead of V1, you can write Q1 over C. Instead of V1, you can write Q1 over C. So you write Q1 over C here. Then you get half Q1 squared over C. So you have different models of equations. Clear? Energy equals half VQ, half CV squared, half Q squared over C. But whatever the equation you use, you get energy. Clear? Whatever the equation you use, you get energy. Clear? Got the idea? Okay. So ideally in questions, okay, they should give us the energy, capacitance, okay, because we can't predict, we can't know that, or we can't predict. So in questions they should give, okay, this is the capacitance of this object, 5 microfarad, like that. But for spheres only we can find the capacitance, because we know a lot of equations related to spheres, right? We know a lot of equations related to spheres. So for spheres only we can write the capacitance. How? Think that you give a charge q to this, okay. If the radius is r, what would be the potential on the surface? On the surface? Potential will be 1 over 4 pi epsilon 1 over 4 pi epsilon q over r, right? Clear? Potential is 1 over 4 pi epsilon q over r. Clear? This is the potential on the surface. Clear? And the charge I know it is q. So for if the capacitance of this conductor is C, I can apply q equals CV. I can apply q equals CV. Then I get q equals C. What is the potential? This is the potential. Potential is q over 4 pi epsilon r. 4 pi epsilon r. Clear? Q over 4 pi epsilon r. That is the potential. Clear? Then this q and this q cancels out. Then C equals what? 4 pi epsilon r. Clear? 4 pi epsilon r. Got the idea? This is the equation for the capacitance. Clear? This is the equation for the capacitance 4 pi epsilon r. Okay. So as you see this, you should understand charge is not there in the equation. Potential is not there in the equation. Capacitance entirely depends on the object. Okay. Not the charge at the moment or the potential at the moment. Capacitance of an object entirely depends on that object. See 4 pi epsilon and r. Everything belongs to the object, right? Permittivity of the object, radius of the object, and 4 pi constant. Clear? So capacitance entirely depends on an object, not the it entirely depends on the object, not the potential or the charge. Clear? Okay. Try exercise 6. 1, 2, and 3. Exercise 6, 1, 2, and 3. A little support, you already know this. In question 2, they are talking about connecting two conductors by another conductor. If you connect two conductors by another conductor, the potential of the two objects will be equal. Potential of the two objects will be equal if you connect two objects by conductors. Try to get answers for these. Just apply Q equals EV, and in some scenarios potential equal means again use Q equals C, Q1 over C1 equals Q2 over C2. Question 1. Question 1 is simple. Question 1. Q equals CV. Q equals CV. I'll just do the first one. So, capacitance of the object 20 microfarad. Capacitance of the object 20 microfarad. Potential. That's what we need to find. Okay, then we should modify the equation like this. Q equals CV, V equals Q over C, V equals Q over C. Then the charge is 5 microcoulomb. Charge is 5 microcoulomb. And the capacitance is 20 microfarad. 20 microfarad. You convert micro into SI, then you get 0.25 volt. Then what about energy? What about energy? Energy is given by half VQ. Energy is given by half VQ, which means half. V means 0.25. V means 0.25. Q means 5 microcoulombs. Q means 5 microcoulombs. This is the energy stored. Clear? Question 2. Question 2. There are two objects. One capacitance is 4 microfarad and the other one capacitance is 6 microfarad. One capacitance is 4 microfarad and the other one capacitance is 6 microfarad. You give a total of 100 microcoulomb to this system. You give a total of 100 microcoulomb to this system and you connect these two by a conducting wire. Clear? So the charge you give will be distributed within these two. Okay, will be distributed within these two. Clear? This one will get a charge of q1, then the charge taken by this one would be 100 minus q1, right? Why? You give a overall of q1 charge to the full system, then this one gets q1, other one gets 100 minus q1. Clear? This one gets q1 and other one gets 100 minus q1. Clear? Okay, so then you apply what? Q equals, then you apply Q equals CV, right? Clear? Then you apply Q equals CV. So the requirement is if two objects are connected by a conductor, their potentials should be equal, right? Which means potential is, for this it is Q1 over C1, for this it is Q2 over C2. Clear? For this it is Q1 over C1, for this it is Q2 over C2. Clear? Q1 over C1 and Q2 over C2. Clear? Same potential. Clear? Same potential. So here the charge is Q1, capacitance is 4. Here the charge is 100 minus Q1, capacitance is 6. Since both sides are micro, I'm not going to convert to SI. Here also all charges are micro, so I'm not going to convert into SI. You solve this, you get Q1. Okay, you solve this, you get Q1. What is the value of Q1 then? Here 3, here 2, then you get 3Q1 equals 200 minus 2Q1. 3Q1 equals 200 minus 2Q1. Clear? Then you get, after solving this, Q1 equals 200 over 5, which means 40 microcoulomb. So Q1 is 40 microcoulomb. Then Q2, charge of this guy is 100 minus 40, which means 60 microcoulomb. Clear? You get 40 microcoulomb and 60 microcoulomb. Clear? Okay. Then energy of on HP is quite simple, right? How? It's not required to find the potential. Otherwise, you have to find the potential if you are writing half VQ. If you are writing the equation half VQ, you have to find the potential. Instead, let's use energy equals half Q squared over C, right? This we have everything, right? We can use half Q squared over C, right? So for the first one, E1 is half, charge is 40 microcoulomb, squared, and the capacitance is 4 microfarad. Then E2 is half, charge is 60 microcoulomb, squared, capacitance is 6 microfarad. Clear? Capacitance is 6 microfarad. Clear? Got the idea? Let's go to question 3. If you are done with 2, done with 3, go to 4, 5 and 6. Question 3. Question 3. Uh, object capacitance 10 farad. Capacitance 10 farad. And the next one, charge of 150 coulomb. Charge 150 coulomb. Connected by a wire. Other one 5 farad. So how much of a charge flow to this side? So if a charge Q flow to this side, then in this side the remaining charge would be 150 minus Q. In this side remaining charge would be 150 minus Q. So V equals Q over C. That means Q1 over C1 equals Q2 over C2. So here 150 minus Q, 150 minus Q over 10 farad equals Q over 5 farad. You solve this, you get Q. What is the answer we get here? 5, 50. So Q is 50, right? Q is 50 coulomb. Clear? That's the amount of charge that flow from this side to that side. Clear? Then you can find energies and all. Okay. And one more theory point I need to do before finishing static electricity part for today. Okay. Write this down quickly. Wait, I'll check the plan too. Okay. So the plan is uh, from next week onwards, like we have to start the new plan, but I received a lot of messages that they have classes only on next week and extra class on next Monday. So from next Tuesday, Wednesday, Friday, we are starting the new plans. So the plan from my side is next week I will have to give a holiday then. Okay, next week is a holiday. Okay, but there's a potential holiday for all the classes. You will miss that, which is on December 2nd week. The classes will get a holiday because I have my convocation. So a lot of work for that. Lot of work in the sense it's a stupid bunch of work. Okay, that means you have to give holiday to a one class and go sign some documents, and there's a specific time for the to sign the document before getting the degree certificate. Okay, then next week there's a specific time to go there just to get the clock and everything like that. I mean, it's just a bunch of useless holidays giving I have to give for the class just for the sake of convocation, and 2 days I have to give for the convocation. So there's a bunch of holidays like that. That whole week I have to give holidays for the classes December 2nd week, but you guys won't be getting that holiday. Okay, okay. So I mean, if I'm giving a holiday next week, I can't afford to give two holidays because I have to keep up with the schedule. Okay, because then if I'm not giving you that holiday, then all okay, everything will be parallel again. Okay, after 2 weeks, so you will have a holiday next day, but you won't get a holiday for my convocation. Okay, I can't even like avoid that. Prize givings I have avoided. I have never gone to a university prize giving. Only once I went, because all other I skipped because I had to do classes. So I skipped all the prize givings for the sake of classes, but can't skip the convocation. My parents would kill me. So, but anyways, there's no point of going for the convocation. You just anyways get the degree certificate. They will deliver it to your home if you're not going there. It's far more convenient. But you know, right? Parents need to go to the convocation. I mean, it's just a bunch of just like stupid stuff. They just keep telling your names in the stage. 900 engineers. Okay, just you have to listen for like 8 hours. People's names. Okay, nothing fun in a convocation. Okay, even in prize givings you have some music kind of stuff, but not in convocations. So you have to just sit there for 8 hours and listen for people's names. Okay, the most useless time in your life, but anyways I have to go for that, so I can't skip that. My parents would kill me. I have otherwise I have skipped everything in the university. No I mean fun stuff I don't skip. I mean prize giving, you anyways get the certificate. Okay, usually in the university they even provide you the PDF of the certificate too, so it's quite convenient not to go to the prize giving. Then you get, I mean next day they send it to your department, so you just collect it from the department head, so it's quite easy. um, but can't skip the convocation. So, but anyways, you are not getting that holiday. I'll give you a holiday next week. Okay, you will not be getting a holiday on December second week, and December last week, as usual, we have to give holidays on all the classes. But since it's Monday and Christmas is on starting on Thursday, I think I may not have to give you a holiday for December last week too, right? Okay. uh, I mean, Christmas starts on Thursday, and if, after the next week, after that, your is on Monday. So there's a 4 days gap between Christmas and our class. So I think potentially we'll be able to do that. Okay, we'll be able to do that. Class two. Okay, so please spread the message. Okay. So next week no classes. Week after that, I'll post the time. Ideally starting at 8 Monday. Okay, ideally starting at 8. I'll inform you the time. Ideally it would be something like 8 to 2. Okay, ideally it would be something like 8 to 2. Okay, but just let me know the issues you have, and you can always skip the heat session and join for the Thursday class heat session. That means you can leave around 12 if you like. Okay, you can leave around 12 if you like, then can stay for the heat session of Thursday, students. Or you can come later for the heat session, and for static electricity you can join the Sunday class. Like that you have different options, two classes going parallelly. The only problem will be for the people who understand English only. They can only move forward with this class. For them only real issues may occur if there are timing issues. Others can have the option of joining either Sunday or Thursday. Okay, or Sunday. Okay, either Sunday, Thursday or Monday. Okay, there's a bunch of options. Okay. So that is the plan. Okay, so next week holiday, but you're not getting any holidays on December. uh, I mean, ideally you won't be getting any holidays on December, but sometimes I may have to give the last week holiday. Have to see about that, but I would try to continue that week too, because then we can finish a lot. Okay. uh, so I mean, ideally you have classes on Monday evening, right? Let's see if the people who come to the class don't have many classes on Monday evenings, we can go until something like Monday evening. So I can finish the syllabus within 2 months or something like that, which would be far more convenient. Then things are done within I mean, the more, I mean, I'm not teaching fast, right? So the more, I mean, we are just getting a lot of time and doing sessions. So I'm not speeding up the class. Okay. So if we have more time, if we can finish things up, you can get rid of this class fast. Okay. 2 months, then it's done. Okay. You can decide not to come to the class after that. Okay. So just don't worry about these 2 months. Okay. The work amount of work you have to do for these 2 months, it's not the whole, it's the whole point is that You do a lot of work for 2-3 months, then when it is close to A levels, you are relaxed. You are done with physics, you have done enough number of past papers, you have done enough number of model papers, you worked on all the areas that you are not comfortable with, you had more than enough time to do that. Okay, then you like go through a very hard time these 2 months, then you get relaxed when it is close to A levels. Okay, that is the ideal plan. Okay, so don't worry if I do a lot of classes, so if I do a class for a longer period of time, it's just a hard time for 2 months. Okay, hard time for 2 months is better than a bit hard time for 8 months. Okay, very hard time for 2 months, then it's done. It's far more convenient than having a bit hard time for the next 8 months. Okay, so let's try to do that. Okay, so one thing is, now capacitors is a very popular term, okay, in electronics. Okay, capacitors is a very popular term in electronics. Clear? So only capacitors is a very popular term in electronics because we need different values of capacitors in different positions. Okay, even like I'll explain that next. So the thing is, when you since now we have considered all the objects as capacitors, right? But the problem is, in electronics you can't use these kind of objects as capacitors, right? You need specific values of capacitors. Okay, okay, for some electronic applications, if it is 5.2046789 microfarad capacitor, that means you need exactly that. Okay, okay, there are some capacitors for like 6 decimal points. Okay, it should be accurate for 6 decimal points, otherwise you can't use that capacitor. Electronics should be that accurate. Okay, sometimes in very complex scenarios like a computer processor. So we need a proper capacitor that we can alter the capacitance. So the solution for that was the parallel plate capacitor. We get two parallel plates. Clear, and provide a charge of q to this one. So if you provide a charge of plus q to this one will naturally get minus q, right? By induction, this one will get naturally, this one will naturally get minus q, right? This is what we call the parallel plate capacitor. Okay, this can hold a very specific amount of capacitance based on how we arrange the system. Clear? Based on how we arrange the system, this one will get a very specific value of capacitance. Clear? Clear? Ah. So if I apply q equals cv here, okay, if I apply I'm capable of applying q equals cv to this one also. Clear? In that case, if you take the total charge of a capacitor, it is 0. Okay, so when you apply q equals cv to a parallel plate capacitor, you only get the charge of one side. Okay, you only get the charge of one side, because otherwise if you take the total charge, it will be 0. Clear? Clear? Then how do we charge a capacitor like this? So assume that you have a capacitor like this, you connect it to a battery. Now what happens? Batteries are capable of moving charges, right? So this battery will take, this is the direction of current, this battery will take positive charges from this side and push positive charge towards this side, right? That's the whole job of a battery. It moves charge, right? So when it put positive charge to this side will be positive, this side will be negative. Clear? This side will be negative. Clear? But this will not continue to happen forever. Why? When more positive charges increase here, the next positive charge will find it hard to reach here, right? The next positive charge will find it hard to reach here. Why? These positive charges repel this one, right? Okay, so it will not happen forever. If the voltage of this battery is V1, it will happen until this capacitor is charged to a potential of V1. Okay, this will happen until this capacitor is charged to a potential of V1. When it is charged, the system actually looks like a battery like this and another battery like this, right? Both providing V1 in opposite directions. Then it will not charge further, right? If you have two opposite batteries, okay, if you have two opposite batteries, a current will not flow, right? So the initially current will flow, initially current will flow, initially current will start flowing, clear? But slowly it will decrease, and after a certain time current will be constant, clear? After a certain time current will be constant, clear? After a certain time current will be constant, clear? Got the idea? Not the current, charge. You get charge from this side, you get charge from this side, but it will not happen forever. When more positive charge appear here, the rate of charge will decrease. Why? The next charge find it difficult to reach here, right? Then after a certain time, it will stop bringing new charge to this side. Then charge will be constant, clear? Then charge will be constant, clear? Ah. Now when you discharge this, what happens? Now you have a charged capacitor. When you have a charge, now you have a charged capacitor. Now you discharge it, maybe through a bulb. Then what happens? When you connect it through a bulb or any continuous path, charge may flow like this and reach here, clear? Charge may flow like this and reach here, clear? And will be neutralized, clear? So for a very short time, the bulb will turn on for a very short time, right? Why? Now you have charge here. Now charge will quickly discharge through the bulb and reach to 0, right? Now the charge will quickly discharge to 0, right? Charge will quickly discharge to 0, clear? Got the idea? Charge will go around and will quickly discharge to 0, clear? Got the idea? It will be neutralized quickly, clear? It will be neutralized quickly. Got the idea? It will be quickly neutralized. So that is the idea. That's how a capacitor works, okay? Now, one small question, what is the point of having a capacitor if it can turn on a bulb for a very short time? We don't use them to turn on bulbs, okay? Why do we use them? Even some short-term memories are also made using capacitors. For an example, can you remember from IT, random access memory, RAM? Technologies are different now. But what is the property of RAM? Can you remember volatile and non-volatile? The RAM is not permanent memory. RAM is not permanent memory. ROM is a permanent memory. Can you remember? Because sometimes memories like RAM use technologies like capacitors. They have millions of capacitors aligned together properly like this. Then you know memory means a bunch of ones and zeros, right? Memory means millions of ones and zeros, right? So it charge a capacitor if it is 1, it discharge a capacitor if it is 0. Discharge, charge a capacitor if it is 1. See? So sometimes short-term memory, there are short-term memory types. It's millions of capacitors charged and discharged accordingly, clear? Charged and discharged accordingly, clear? It's millions of capacitors. Okay? It contains millions of, like it contains millions of capacitors that hold ones and zeros. That's why this disappears when we discharge when we remove the computer from the plug. Why? This charge disappears when there is no power, right? The whole charge disappears when there is no power, right? Clear? That's why it erases its memory when we turn off the switch. Clear? Then at the same time, sometimes these are used for protection. That means if your computer motherboard tells that it works by 12 volt, it should be exactly 12 volt. 12.1 sometimes can burn it, 11.9 can sometimes burn it. Then in the motherboard you have the computer processor, very sensitive chip. If the processor manufacturer tells that this works by 5.00005 volts, 5.00051 will burn it. Okay, 5.0049 will burn it. Okay, processor is that sensitive. So you can't afford voltage fluctuations. Okay, you can't afford voltage fluctuations. So in the power input of your computer motherboard, there you have a lot of capacitors. We call these capacitor banks. What happens is, assume when your computer motherboard is exactly getting 12 volts, these capacitors may charge to 12 volts. Okay, these capacitors will charge to 12 volts. Clear? These capacitors also will charge to 12 volts. Now assume due to a sudden power shortage, or there are definitely in our power grids, there are power issues. Someone pulls the plug out of the laptop, some kind of a scenario, okay? Some kind of a scenario, okay? If a small voltage fluctuation happens, voltage fluctuation means a current fluctuation, right? If the voltage fluctuations, why the laptop burns, why the motherboard burns? Due to the current fluctuation. But that small decrease of current will be protected by the capacitor by giving the stored charge for a very short time. So this, when the voltage goes down, the current will decrease a bit, but the motherboard will not feel that. Why? Capacitor will provide its stored energy to the motherboard quickly. Clear? Then the motherboard will keep working like that. You can find thousands of capacitors in any electronic system. Clear? You can find thousands of capacitors in any electronic system. Clear? Got the idea? That is the main usage of capacitors. Got the idea? So next week we have to analyze properly the usage of other like capacitors and kind of stuff. Okay, so let's start the heat session maybe around 6:32. 10 minutes break. Okay, let's start around 6:32 the heat session. Okay.